solve this? Well, let's just think about which papers could coincide with each other and which ones couldn't. For example, we know we better not have paper A at the same time as paper C, because then poor old candidate number 1 would be trying to do 2 papers at once, and that we don't insist on. Similarly, B can't go with D, A can't go with G, A can't go with C, D can't go with E, and so on. Well, it's a bit annoying looking at this table here, so I just want to sort of represent that knowledge in a slightly more convenient form. I'll just draw a little thing here. So what I've done here is, this is paper A, and I've drawn a link from A to C to say that A and C are incompatible because candidate number 1 is taking them both. So when 2 papers cannot go together, I've joined them with a link. When they can go together, I haven't joined them. Now, what are we trying to do? We're trying to associate, well, let's say we're trying to do it in 3 sittings. So to each paper, we'll say, well, it'll either be the first sitting, second sitting, or third sitting. So to each of these nodes here, we'll associate the number 1, 2, or 3. What must we not do? We must not have 2 incompatible papers in the same sitting. So for example, we mustn't have 1 with A and 1 with C. Well, it's a little bit inconvenient having 1s, 2s, and 3s. Might be nice if we just put a bit of color into it and said 1 is, say, what was it, red, 2 was green, 3 was blue, or something like that. So now what are we trying to do? We're trying to color these circles in with 3 colors in such a way that you never have the same color at either end of one of these links. That problem, I hope, will remind you of something. So it can be done. So any non-mathematicians were sitting there thinking, why on earth do mathematicians worry about coloring nodes of networks? Seems a rather strange thing to do, coloring things in, a bit childish. Well, actually, it's exactly the same problem as timetabling, and timetabling comes up in many contexts. And in fact, I would say more. You can transform this kind of problem much, much more than I've done. But maybe that will be discussed later on. So I think I've said enough on the economic case for supporting pure mathematical research in more or less its current form. And I would now like to turn to the cultural case. I, as I have said, am one of those individual mathematicians who do not directly strive to swell the national coffers. So let me spend some time explaining what it is about mathematical research that so appeals to me. Since mathematics is a very broad subject, and tastes and mathematical styles differ widely from one branch of this subject to another, this part of the lecture will inevitably be less universal and more personal than the first. However, I believe my experience is fairly typical. I hope that in France, of all places, a cultural argument will be taken seriously. My home country, England, was famously described by Napoleon as une nation de boutiquiers, a nation of shopkeepers. In England, the word intellectual is sometimes regarded as virtually a synonym for pretentious, whereas in France, intellectuals are widely admired and abstract thought greatly appreciated, or at least so one reads. The cultural case, in brief, is that knowledge is worth pursuing for its own sake. Just as one of the rewards for individual mathematical or other cultural success is a form of immortality, so entire societies, ancient Greece being the most obvious example, are remembered for their contributions to knowledge long after their political and economic influence has faded. A society that deliberately turns its back on the pursuit of knowledge is, to put it bluntly, a boring society. On the other hand, it would be foolish to suggest that all knowledge, or even all mathematical knowledge, is of equal value. What I shall do now is talk a little about a theorem that I definitely do find worth knowing for its own sake. Perhaps one day it will be useful as well, but for now, I present it as an example of beauty in mathematics. The idea that a piece of mathematics could have an aesthetic appeal puzzles those who have never experienced it, or perhaps I should say never knowingly experienced it. The theorem I've chosen as my example is very well known in the right mathematical circles, but it is not one of the giant theorems of the 20th century and is completely unknown outside mathematics. This is a deliberate decision on my part because I want to make the point that mathematical beauty is not confined to 1 or 2 spectacular and famous theorems, but lurks everywhere, waiting to surprise and delight us. So here comes another lot of numbers. Is there room for it? Not quite. Well, those are the numbers from 2 to 100. It's not immediately apparent that that's what it is, but if you do the sums that I've indicated, you will find that it really is the numbers from 2 to 100 in that order. So we go 2, 3, and then 2 by 2 is 4, 5, 2 times 3 is 6, and so on. So what I've done is write the numbers from 2 to 100 in their prime factorizations. I take each one and write it as a product of primes. And next to it in green, I've just written how many primes I needed. Let me just read out the beginning of that sequence. It goes 1, 1, 2, 1, 2, 1, 3, 2, 2, 1, 3, 1, 2, 2, 4, 1, 3, 1, 3, 2, 2. So is there any pattern that one can spot there? I don't know. It's not really... if you could really spot a sort of simple pattern, then probably you would have made a mistake, but if not, you'd become very famous. It seems somehow rather sporadic and difficult to make head or tail of it. Well, in order to make head or tail of it, what I decided to do was just to count up how many of these numbers needed one factor, how many needed two factors, how many needed three, and so on. So a number that just needs one factor is precisely a prime number, whereas a number that needs 6, which happens twice with 64 and 96, is a product of lots of small prime numbers. And so here's a little table. 25 prime numbers, 34 numbers had 2 factors, and so on. And underneath I've just drawn a bar chart which encapsulates the information in the table above. Now, even a non-mathematician, if he's feeling particularly speculative, may notice something about the shape of this bar chart. It goes up, and then it goes down. But when it goes down here, it sort of slightly levels off at the bottom. This is a fairly familiar sort of shape. It's the well-known bell curve that comes up in probability. So it's sort of tempting, maybe a bit silly, but tempting, just to try to fit a bell curve to this thing. So that's what I've done here. Now, you could object to that, saying that the bit on the left is not very realistic. But 100 is a small number, as mathematical numbers go. And if you were feeling really sort of well, if you're just in dreamland, you might think, perhaps if you took a much bigger number, it would get a bit closer to a bell curve, and a much bigger number still. Well, this thought occurred to somebody called Katz, and he was a probabilist, so somehow the idea of a bell curve seemed reasonably natural to him. But it wouldn't have seemed natural to a number theorist in his day, because somehow the prime numbers are completely deterministic. Why should probability have anything to do with them? And he couldn't prove that the bell curve had anything to do with it, but he went and gave a talk in the Institute for Advanced Study in Princeton, and by good fortune, Paul Erdős was in the audience. He didn't seem to be concentrating all that much, but that never meant anything with Erdős, because by the end of the talk, he said he could prove that the bell curve did indeed genuinely occur. I'm not going to say much about this slide, but let me just say that it was known that the average number of prime factors